When we start to look at how something can decay radioactively, or even if it can, there are a variety of laws that tell us what's allowed and what's not. Two of the big ones: energy has to be conserved, of course. We've had that since you started studying physics. Uh, this is what keeps protons from being able to decay into neutrons, because the proton is a little bit smaller. A free neutron can decay into a proton, but it can't go the other way because energy wouldn't be conserved. Charge also has to be conserved. So if that neutron does decay into a proton, it's going from zero charge to plus E charge. Something else has to be involved that gives us a charge of minus E. So that would be like an electron in this case. These two conservation laws have never been violated. So it would be a very big deal for physics if something violated them. A little bit less crucial, we have conservation of baryon number. The only baryons we're going to talk about in this course, baryon means heavy particle, protons and neutrons. They are both assigned a baryon number of plus one. Antimatter versions of these, so antineutrons or antiprotons, would have a baryon number of minus one. So how does this work for an alpha decay? Something that alpha decays is uranium 238. We use the same kind of notation you see in chemistry, where you have the input on the left and then an arrow and the output on the right. So if 238 is going to alpha decay, we know that on the other side of the arrow we've got an alpha particle, but what else? Well, we can write the proton number and nucleon number on the alpha and uranium. Uranium is 92 protons. U-238 is 238 baryons altogether. The alpha particle is 4 baryons, 2 of them are protons. So what's left? Well, it's got to be something that has 238 minus 4, 234 baryons, and 92 minus 2, 90 protons. So 90 protons is thorium. So what this means is the only thing it can decay into is thorium-234. So remember, the 4, the 234 together give us 238. 90 plus 2 gives us 92. Alpha decay is really common for the very heaviest elements. These are the ones that settled close to the Earth's core when the Earth was liquid. So what happens when there's radioactive decay in the center of the Earth? Aside from it keeping the Earth warm for billions of years so far, these alpha particles will grab a couple of electrons to neutralize themselves, and that'll make them helium atoms. Now the helium would like to get out into space, but it's stuck underground a lot of times, and it gets freed when we go looking for natural gas. There is no other source of helium on Earth, and we can't make it, at least until fusion is developed. We could get all the hydrogen we want by separating it from water or something else, but since helium doesn't combine with anything, all there is free helium, and the only source of it is the alpha particle decay. Uh, it's kind of a important material in terms of the different things we use it for and our inability to make it. So it's a little bit crazy that we still put it in balloons instead of something like hydrogen when we're using helium for MRI machines and other important things. And yes, hydrogen is flammable, but a balloon the size of your head full of hydrogen is not going to kill people when it catches fire. Uh, just removing protons and neutrons at equal amounts, though, won't give us stable products if we keep taking 2 of each. Because let's say this just kept going. We start with uranium-238 and we go through 20 alpha decays, which doesn't happen, but if it did, then we would have lost 80 baryons altogether. So we go from 238 to 158, and we would have lost 40 protons. So we'd be down to 52 from 92. So this would be tellurium-158. The heaviest stable isotope of tellurium is 128, which is 30 fewer neutrons. So we can't keep doing it like this. It's not energetically favorable to keep pulling alpha particles out of this thing. So we have to have some way to fix the neutron to proton ratio, because remember, up here in the heavy part of the periodic table, we're 3 to 2, but we have to get back down to 1 to 1 as we make our way to light elements. So Just removing equal numbers of both protons and neutrons can't do it. And this is what beta decay does. That will let you turn a neutron into a proton or vice versa. You may have heard of carbon dating. It's typically carbon 14 dating, and what happens there is a carbon 14 nucleus. You see that the 6 is going to a 7, so that means a proton has been created. We see the number of baryons hasn't changed, so what's happened is a neutron has turned into a proton. And to balance charge conservation, this electron gets kicked out. So we had 6 positive charges here. Here's 7 positive and 1 negative, so charge is conserved. Baryon number hasn't changed. It has to be conserved. We've got 14 on both sides. The electron isn't a baryon, so its baryon number would be 0. Usually rather than beta, what you put in is the standard symbol for an electron, so we might write it like this. However, this is still not a complete expression. The charge conservation is okay, energy conservation is okay, baryon number conservation is okay, but there's also something called lepton number, which has to be conserved. Leptons, that means light particle. Electrons have a lepton number of +1. And now we've got a problem because lepton number of this carbon and this nitrogen are both 0. So we can't just spontaneously go from lepton number of 0 to 1. So we got to have something else on this output to cancel out the electron's lepton number. It can't be an anti-electron because that would cancel out the charge too and screw that up. It turns out besides the electron and some heavier cousins, the other leptons are neutrinos. That's not a neutron, but a neutrino. These things are uncharged, and they have masses much, much smaller than even the electron's mass. So there's a neutrino associated with the electron, with the muon, with these other particles. And of course, it's called the electron neutrino, and we write it with a Greek nu with a subscript e. Now, this has a lepton number of +1, so this wouldn't help. If we added one of those, we've just got lepton number of 2 on this side and 0 going in. So what we really need is the antineutrino, and we indicate that by putting a bar over this. So the real decay for carbon-14 dating is we get nitrogen-14, an electron, and an electron antineutrino. This is also what we would see if we had a neutron just hanging out by itself. So neutron by itself will turn into a proton. Notice that baryon number is conserved. Charge is going to be conserved because we get 0 here and 1 plus minus 1 here. And then lepton number is conserved, 1 and minus 1. One common decay that you see in the nuclear medicine clinics and hospitals for PET imaging is when fluorine-18 decays into oxygen-18. Now, what else is going to be produced when that happens? Well, if we look at this, we're okay for baryons. We don't need any of them. But we're going from 9 protons to 8. So we have to have something that's positively charged here and not a baryon. And what that gives us, what that leaves us with is the positron, or the antimatter electron. So that appears on the right side, but now that screws up the lepton number. It gives us -1 on the right for the positron. We have to correct it without changing the charge or baryon number, so that's a neutrino. So here's the real decay. 18 baryons on both sides, 9 positive charges here, 8 plus 1 here, 0 baryons on 0 leptons on this side, 0 here, -1 here, +1 here, so 0 on the right. Now, these neutrinos or antineutrinos, whichever decay you're talking about, virtually never get detected. They don't carry charge, so they don't feel the electromagnetic force. They don't feel the strong force, and gravity does almost nothing on this scale, so it might as well not even be there. It interacts through something called the weak force, or the weak nuclear force. If you have the entire Earth as your radiation shielding and you fire 10 billion neutrinos through it, 1 would be expected to be stopped. They were predicted before they were discovered because they do take away some energy, and it looked like, if you can't see this piece, If you just see this and the positron, you'll notice energy doesn't seem to be conserved sometimes. It seems like you have a certain amount of energy here and this is less. So you can't see these things, but the choices that people had back then were either to say, well, okay, I guess energy conservation doesn't work on the quantum level, which would be pretty scary for physics, or there's some particle we're missing. Now, these things have been detected since they were predicted, but again, it's really, really hard. You need detectors that contain many, many tons of material, and they get only a very small fraction of the neutrinos that pass through. The last kind of decay, finally, is gamma decay. And this is sometimes a previous decay will leave a nucleus in an excited state. And this excited means the same thing it does for an atom if we move the electron to one of the outer states rather than the ground. Those excited atoms, that electron wants to get back to ground and it has to emit a photon. The same kind of thing happens in the nucleus. It wants to get back to its ground state. But instead of throwing out a photon of a few eV like an electron would do, the nucleus is going to throw out a photon of a few MeV because the nuclear energies are in the ballpark of 1,000,000 times electronic energies. So we get gammas out instead of visible light. The way we usually represent an excited nucleus is with an M for metastable or with an asterisk. What metastable means is the excited state that it sits in lasts a long time compared to similar states, but not necessarily a long time on our scale. Again, the most common example of this is in a nuclear medicine clinic. If you've ever known anybody who had to take a stress test, maybe they had chest pains, they have to go to the hospital, they get injected, they have to ride a bike or get on a treadmill, and they get imaged a couple of times. And what they're using, which we'll look at later, is almost certainly going to be technetium 99M. So it's written the same way we'd expect, 43 for the number of protons, 99 for the number of nucleons, and M for metastable. And when it decays, notice baryon number, nothing changes over here in terms of the conservation or the conserved quantities that we talked about, except we get the energy out. And this gamma has an energy of 140 keV. So we didn't change charge, baryon number, or lepton number. All we did is take the nucleus from an excited state to a more stable state.